Welcome to MEI Numerical Methods, Solution of Equations 2. In this video we'll be comparing the various methods for solving equations numerically. Now, as far as speed of convergence is concerned, the Newton-Raphson method is usually the best, closely followed by the fixed point method, but it depends what the value of the derivative of g of x at alpha is. So if that's close to 0, then the fixed point method will be a good method. And in fact, the Newton-Raphson method can be shown to be a special case of the fixed point method, where g dash of alpha is actually 0. So that explains why that's at the top of the list. If we haven't got g dash of alpha that close to 0, then the secant method can sometimes be better, but it's usually the fixed point method is better than the false position method, which is usually better than the bisection method. Now, as far as reliability is concerned, assuming there is a route to converge to, so assuming we haven't got a discontinuous function or that the route is repeated, then the bisection method and the method of false position can be relied on to converge to that route. Whereas this isn't the case for the secant, Newton-Raphson and fixed point methods. And we've already seen that the fixed point method can break down if we haven't got a suitable rearrangement and there isn't any convergence. Though we have got the option of trying a relaxed iteration to turn the rearrangement into one that does have a value of g dash of alpha between -1 and 1. And then we've got the problem with the bisection method, where there may be more than two routes, and we find one of them, and we overlook the possibility of there being another one. Then we've seen with the Newton-Raphson method that if our initial value is close to a turning point, then the tangent is going to shoot off well to one side and could in fact go outside the domain of the function, or could just be too far away from the root to be of any use. And of course this could happen at any point, so I've mentioned x1 on the screen here, but of course this applies to any value of the estimate. And also at any stage with the Newton-Raphson method, there's always a danger that our estimate, either x1 or a later estimate, could stray away from the route that we're looking for to another one that we've already found, perhaps. Now, we've seen that the Newton-Raphson method and the fixed point methods can both be carried out very quickly with a calculator. And we've also seen that for the bisection method and the false position method, we've got to be looking for a change of sign at each stage, so that makes them quite time consuming. And for the bisection method, we've got the additional drawback that we can get lots of decimal places occurring in the figures. Now, there's also the issue of whether error bounds are automatically provided by the method. So that's the case for the bisection and false position methods, but not for the secant method and Newton-Raphson methods, where we would need to create a bound for ourselves and use the change of sign method to check that we've got an interval in which the root lies. And then for the fixed point method, if g dash of alpha is between -1 and 0, then we're going to have cobweb convergence, and so we're alternating between being either side of alpha, which means that we've always got an interval for alpha whenever we decide to stop. So that concludes the videos for solution of equations 2.